Hello, in this video we'll be going over plane geometry. In the previous video, we saw how there are many different types of geometry. Plane geometry is going to be one of our more significant ones, and we'll see how many important themes are brought up, like what it means to be on opposite sides of a line, or how we're able to measure lengths or angles. A lot of these ideas will be very prevalent in many of the other future geometries we'll be covering. Unlike our previous videos, our undefined term list looks a little different. We're familiar with the terms point and line, but for the rest of the terms, we'll be covering it with a related section. However, we're not going to be covering over area right now. Plane geometry has many definitions and theorems as well, so I won't be covering over all of them, but I will be showing some of the more relevant ones. I would suggest practicing visualizing or proving them to get familiarity with the structure of proofs and how the information relates to each other. Our first section will be covering over the two fundamental axioms, the existence and incidence postulate. Our first axiom is very trivial, but is only needed to help us rule out any assumptions. The second axiom tells us that there is a unique line that goes through 2 points. This axiom may seem very simple, but is actually very important to help us understand how lines will intersect. Most of our definitions will be very simple, as you can see on our right, and they'll just tell us how we define certain terms. It'll be important to take note of the notation being used, as we'll frequently be seeing them later on. Let's take a look at our first theorem. If L and M are two non-parallel lines, then they only intersect at one point. If we go back to what the meaning of a theorem is, it is a proven statement. So how exactly did we get to this notion? Let's try to prove this ourselves, this time with contradiction. This means we'll start off by assuming that we have two lines, L and M, but this time they touch each other more than once. If we remember from our incidence postulate, two non-parallel lines can only intersect at one point. Therefore, this creates a contradiction, which means there can only exist one point where they meet. This first proof may seem very intuitive, but it's important to practice using deductive reasoning to get where you want. Sometimes, what seems obvious may not be true in all cases. It takes deep understanding of what you're able to do with the given axioms and how to make sure there's no way to go around. This next section will be covering over how we define distance and the uniqueness of these lengths so that we're able to compare them to each other even when they're on different lines. Similar to its name, the ruler postulate tells us that there's a unique distance between 2 points on a line and that we can calculate it. This implies that this distance has a correspondence to real numbers and is also continuous. I do want you to take note that there's many different ways to represent distance. And even though the ruler postulate has the word distance in it, it is directly referring to the length of the segment. With these set of definitions, we get to see a peek of what it means for things to be congruent or equal. This is very important to recognize because we'll be frequently comparing the size of different things. We rarely care about the quantifiable nature of objects because we want to know if these statements hold true for all cases. Moving on, Theorem 2.2 tells us that there exists a unique midpoint, and Theorem 2.3 tells us that there exists a unique point a certain distance away from the endpoint of a ray. Let's go more in depth for Theorem 2.2 and prove it using what we know about lengths. We'll prove this by contradiction, assuming that there exists more than one midpoint for the line AB. Let's use the points M and N as our midpoints. Since M and N are unique, using the ruler postulate, we can define the line as the sum of AM, MN, and NB. Since both M and N are midpoints, this implies that the measurement of AM is the same as AN. This makes our new sum for the line AB to be AN, MN, and NB. However, this is a contradiction because AN plus NB also equals AB. Therefore, M and N would have to be the same point for them to be midpoints. This next section will be covering what it means to be on opposite sides and how that interaction creates intersections. The definition of a convex set isn't too important for this, but it's basically a space where each pair of the points inside can form a line. If we want to look at how this interacts with the plane separation postulate, we can start off by just imagining that we have a line that splits our space into two sections, kind of like a wall, forming half plane 1 and half plane 2. These half planes should never share any space. If we have 2 points and they're on the same side, or where both points are in the same half plane, the line PQ will never intersect L. If they're on separate sides of a line, or in different half planes, PQ will intersect L. Now you may be thinking, this is a bit too much just to specify that lines are intersecting each other. But without this, we could have cases where they look like they're touching each other, but don't actually have an intersection. Or we could just have another case where a line goes through a gap where there's no points on that line and also not creating an intersection. So this axiom just really solidifies the notion of intersection by comparing 2 points on an object, and that we can't somehow squeeze through or go over the lines without touching. Our next definition is pretty important to understand. In our definition for angles, realize that they're defined from two rays. These cannot be opposite rays. We can see why with our next definition. Let's draw a quick sketch of what an angle would look like conceptually so we can see why they cannot be opposite rays. We can extend one of the rays to make a half plane so that it contains the point from the other ray. And we'd do the same thing for the other side. We can see how there's this overlap. This is what we would define as the interior. For a straight angle, this would not be possible because we would not be able to make a half plane that contains the other point because it would be on the line itself. A ray theorem is pretty simple. It just tells us that if we have a ray, it won't go on the other side. But let's try and prove this. We can prove this by contradiction, assuming we have a ray so that C lies on the opposite side from B. Since C and B are on opposite sides from the plane separation axiom, they must intersect through point A, or some other point on L. In our first case, this can't happen because we said A is our endpoint, so we can't just intersect at A. And for our second case, our incidence postulate told us that there can exist only one line that goes through 2 points. So this would also get us a contradiction as well. This means B and C would have to be on the same side of L. For Theorem 3.2, it tells us that for a point to be between B and C, the ray AD has to be between rays AB and AC. This applies vice versa. We'll also be proving later on why this works. For Pasch's axiom, we've already seen this in a previous video, and it states that if a line enters through one side of the triangle without going through any of the other vertices, it must exit through one of the other sides. Going back to Theorem 2, we'll start with 3 non-collinear points, and we know that D exists somewhere on the line BC. Well, if we draw the line AC using the ray theorem we just solved, if we draw a ray CB, we know that B and D are on the same side. We'll get a similar result when we draw the line AB and the ray CB. We will see that C and D are on the same side. Now, if we recall the definition of what it means to be on the interior, it is the intersection of half planes created by arrays. We know D is on the interior of AB and AC, so there exists a ray AD that is between the two rays. To fully prove this theorem, we would also have to do it the other way around, but I'll leave that to you. In this next section, we'll be covering angle measurements and how they define equivalency. In this and future videos, you'll see a lot more focus on measurement and comparisons between side length, angle measurement, and even shapes. I want you to look at the similarities in the axioms and theorems for this topic, and even the similarities in the proofs. These are usually near identical but use different terms. Looking at the postulate itself, the protractor postulate is very long and is very similar to the ruler postulate, but this time we're dealing with angles. It basically just says that there exists a unique angle such that we're able to construct it. In the previous section, we saw a definition and theorem which related to how we define a for rays between other rays. But in the betweenness theorem for rays, this uses angle measurement to determine betweenness. Similarly to the uniqueness of a midpoint, we have a uniqueness of an angle bisector, though this time we will be proving for the betweenness theorem for rays. We can start off the proof by assuming ray AD is between rays AB and AC. By using the protractor postulate, we note that the measurements of angle BAD and DAC is equal to the measurement of angle BAC. Well, using algebra, we know that the whole has to be greater than the part, which proves the first half. In this section, we will not be going over any axioms, but we will cover some of the more important theorems, which will be very useful in later proofs. Some of the main theorems in this section are the Z-theorem and the Crossbar theorem. The Z-theorem tells us that if we have two rays with different endpoints and on different sides, they will not intersect each other. And the Crossbar theorem tells us that if we have a triangle and a point inside one of the interior angles, it will intersect the opposite facing side. Now, this may seem very similar to Pasch's axiom in the way that if we have a line going through the triangle, it will go out through one of the other sides, but we'll actually see later on how this theorem is much more useful. This theorem helps us guarantee the intersection of a line segment when extended. This theorem helps guarantee the intersection of a line to a segment when extended from a vertices. We will only focus on proving the crossbar theorem. For this one, we will start off with a point D on the inside of a triangle. From our previous axioms, if we wanted to extend the rays AB and AC, we know that there exists some other point on the ray AD, but is past the segment and is still between the two rays. Now we can see D and G on opposite sides of BC, so there is a point of intersection on that line, thus giving our proof. Another important theorem is the linear pair theorem, which tells us that if angles form a linear pair, then the measurement of those angles is equal to 180 degrees. As referenced earlier in the video, we don't call it a straight angle, but rather a linear pair because of how they are opposite rays. Just like our bisector and midpoint theorems, we also have a theorem for perpendicular lines and another for perpendicular bisectors. Like we've seen for the other ones, the proofs will look very familiar for these two. We'll prove the uniqueness of perpendicular lines from a point. To start the proof, we'll assume that there exists a line with a point P on it, and there also exist two lines M and N that go through point P but are both perpendicular to L. Now if we look at the angles to see what makes up the line, we have two right angles from perpendicular lines, but then also the angle between them, since M and N are distinct. However, if we add all of these angles up, we'll get more than 180 degrees, which is a contradiction. This means that there can only be one distinct line through P. To close this section, we'll have some theorems and definitions relating to vertical angles, but I won't be covering over them right now. Moving to our last and final section, this one focuses on what we define to be congruent to each other. This is a very important section because this is what allows us to compare shapes not connected to each other, and also show identicalness. We'll see how the sides and angles interact to give us congruencies. As a side note, when writing down these proofs, pay attention to the notation and the order of letters. For example, angle ABC is not the same as angle CAB. Make sure to keep track of the reference of the points that you're using, and try to be consistent on the order of direction, labeling everything clockwise or labeling everything counterclockwise. The last axiom we'll be looking at for plane geometry is the SAS congruency. The reason why this congruency is so significant is because it not only tells us what shapes are congruent to each other, but also allows us to move stuff without changing them. It is important to realize that this is not the case for all geometries, and sometimes there will be distortions depending on how it's moved. In plane geometry, as long as the corresponding side lengths, angles, are the same, we can do all sorts of transformations, like reflections, translations, and even rotations. As a short exercise for closure, we'll look at isosceles triangles and how to prove the isosceles triangle theorem. We will first start off by making a triangle such that two of the side lengths are the same. From our bisector and crossbar theorem, we're able to make a line that bisects our top angle and go through the bottom of the triangle. We have two lines, the AB and CA lines, that are congruent, along with our bisected angle BAE and CAE. With this bisected line, it creates two triangles that share the same side. Well, given our SAS axiom, we're able to identify that triangles ABE and CAE are congruent, which means that the base angles are also congruent, thus proving our theorem. As a closure, there are many important topics that were covered, ranging from what we define measurement, lines, or even angles to be, and also how we identify congruencies. Plane geometry is not very commonly used, but the way that we approach many of the proofs in this topic are very notable and will be seen very frequently in other areas. As stated previously, try to find commonalities in how certain topics are defined because many of these function in similar ways. I hope you enjoyed the video, and I'll see you next time.